These problems get even more exciting now. We get to use the washer method. So this expands the types of problems that we can solve. Just like always, I've got to start with the picture here. We're going to find the volume of the solid formed by revolving the region bounded by the graphs of the equations about the x-axis. That's good to know. So let's do a little picture here. So I've got the square root of x, and then I'll have y equals 2 and x equals 16. So the region that got enclosed there was just that little bit. That's the bit that got enclosed. And we're going to revolve that around the x-axis. And so if you can imagine that shape, you're going to have something with a hole in it because we have this gap here. Right? So that's why I'm going to use the washer method instead of just the plain old disk method. And so the thing with the washer method is you're going to have an outer radius and an inner radius. And this is where that representative slice becomes far more important. So when I imagine the slice here, I'm going to think about two different places here. Right here, this is going to be the big radius. Right? So from here to here, what is that radius? And I can see that that's the height of the function. So this is going to be my r of x. And then you have from here to here, the little radius. Right? This is the whole. What do I need to subtract? And I can see that that's the same everywhere. It's just that line, y equals 2. So there's my r of x. So now when I get ready to set up my integral now, this is going to be pi times the integral from, where were we? I need to know what that intersection point is. I need to know what a is. So where will y equals 2 equal y equals the square root of x? I'm going to say that's when x is equal to 4. Square root of 4 would give me 2. So I'm going to integrate from 4 to 16 of the big radius, and remember that was just the function, so the big radius squared minus the little radius squared. So I'm taking the large disk minus the small disk. That's what's happening here. And this is all with respect to x. Again, that's the hardest part of these problems, is setting it up. Once you've got this integral set up, it's smooth sailing. You know how to integrate, it's just tedious work at this point. So I will clean this up before I try to integrate. So I've got pi times the integral from 4 to 16 of square root squared. Makes that go away. That was convenient. 2 squared is 4. That's not too shabby. I can do that. So this is pi times x squared over 2 minus 4x. I'm going to evaluate that from 4 to 16. And again, it's just tedious plugging those things in, but we can do it. If I plug 16 into this, I'm going to get 64. And if I plug 4 in, I'm going to get negative 8. And yes, I did that arithmetic earlier because that's not really the point of this lesson. You get 72 pi. Let's do another one. Find the volume of the solid formed by revolving the region bounded by the graphs of the equations about the y-axis. So y-axis, that's my red flag. I'm going to have to solve both of these for x at some point. Let's go ahead and graph this. And again, if you need to, you can go ahead and graph these. I know here I've got y-intercept at 1, and it's going to be a pretty low slope there. And then steeper slope for this one, and then y equals 3. And so this region, that got pretty messy, but it's this region right in here. And we're going to revolve that around the y-axis. So here's my representative slice. And again, I'm looking at the endpoints of this. This endpoint's going to give me the big radius. This endpoint's going to give me the little radius. And so I see that the big radius there is going to be, that was my function that wasn't as steep, that's this one. There's r of y. But I'm going to have to solve it for y. So let's do that. I've got y minus 1, and then I multiply the whole thing by 2. That would give me that function in terms of y. So I've got 2y minus 2 here for the big radius. And then this little radius, that's just the distance from there to there. That's this steeper function that we had. That was this one. This one's going to be little r of y. And so again, I'll solve that for y. I get y minus 1 divided by 3. So little r is y minus 1 over 3. And then I need to figure out what my limits of integration are. Here, when I plug 0 into both of those functions, I get 1, and then we have y equals 3 for our upper limit. That gets a little bit messy, but again, all you're looking for here is you're looking for that big radius and then that little radius and assigning a function to it. I'm ready to set up my integral now. So this is pi times the integral from, I messed that up. Okay, hear me out, just hear me out. This is supposed to be a 7. This was supposed to say y equals 7, right? It'll change all my arithmetic that I've already done if I don't fix that. Not a big deal, just pretend that that was a 7 there. Nothing else changed, everything is totally fine. We're doing the integral from 1 to 7. Everything's fine. Of the big radius, so that was 2y minus 2 squared, minus the little radius squared. That's the hardest part. If you can get that set up correctly and not make typos and not make mistakes, then it's smooth sailing for the rest of it. I shouldn't say smooth, I should say it's not challenging. It's going to be very tedious because I need to expand this thing before I can integrate. I guess I could do u substitution on all of these. I didn't think to try that earlier. You should do that. You should try these with u substitution. I'm going to go ahead and expand it just because I'm looking at my notes here, and I will make a mistake if I don't follow my notes. But you try that. You go do u substitution. I'm going to work it out my way. We'll see if we get the same answer here. So when I expand this, it gets gross. So I've got 4y squared minus 8y plus 4, and then I took that 1/9 out front here. So I just had to worry about the y minus 1. I get y squared minus 2y plus 1. And I would really like to combine like terms here because I feel like it'll simplify nicely, but that pesky 1/9 means I have to go through everything here and multiply it by 9/9. When I do that, I get pi, the integral from 1 to 7 of, okay, so I'm giving everything a common denominator here, basically, is what I'm doing here. And you're probably already done with your u substitution at this point. You've already integrated. And then I'm distributing my negative 1/9 through the rest of these terms. But the reason I wanted to do all of that is because I do have common terms here now that I can combine. So that gives me 35y squared over 9 minus 70y over 9 when I combine those, and then plus 35/9. So then I only had 3 terms that I had to integrate here. I liked that a lot better. So when I integrate that, I get pi times 35y cubed over 3. So I'm doing the 9 times 3 gives me 27. And then 35y squared over 9. So when I divide by the 2, that 70 goes away. And then plus 35y over 9. And I'm evaluating that from 1 to 7. You're done. You're waiting for me to get here. When I plug 7 into this monster, I get 75/95 over 27. What the heck? Minus, when I plug 1 in, I get 35 over 27. And that comes out nicely. It comes out to 280. 280 times pi. Anyway, these problems are beastly. They really are. But the point of them is the setup, right? Is identifying that big radius, identify your small radius, and then it's just the integral of the big radius squared minus the little radius squared.